so let's just head back to where we ended. Um, Actually, this part, what you're seeing right now, that's for the second long exam. Um, Although in your institution, it may be a different exam, obviously. Um, it's just in the way the lessons were taught to us chronologically. This is meant for long quiz too. So molecular speeds, molecular velocity, um, the kinetic theory of gases, etc. So we will go here. Um, I think we stopped here. I think, yeah. In the difference between effusion and diffusion. So let's now move on to molecular weight determination. There are basically three methods. So we have Regnald's method. This is specifically to determine the molar mass of gases at room temperature. So essentially, when a word problem mentions of um, basically there's a mention of a dry bulb, uh, the gas itself, obviously. Um, that's obviously expect that in every kind of question. But specifically for this method, a dry bulb is mentioned, specifically its mass. Also, you have the mass of the dry bulb plus the gas, given a temperature and the pressure, and the mass of the bulb plus the liquid, such that the density is known. This symbol, that's raw. Okay. At this point, it's important that you know the symbol. Okay, so an example problem is this. So a dry gas bulb of for 300 to 500 ml capacity is evacuated and weighed. At a definite temperature and pressure, the bulb is filled with gas and weighed. And the bulb is then filled with a liquid of known density and weight. So typically this is what you will read in the problem, no? So what do we have here? For the mass of the gas, okay. Um, to identify the volume of a liquid, coming from this relationship, V is equal to M over density. In other words, density is mass over volume, no? So from that relationship, we have this mass of the liquid over density of the liquid. This is supposedly the volume of the gas as well. Why is that? In a dry bulb, that's basically an example of a fixed container. And regarding the properties of liquid and gas, if there is a container, then basically the volume is gonna be the same. Actually, that's actually mentioned here. Um, Unfortunately, it's not. It's gonna be hard to read from where you are, but it's basically this. For liquid and gas, um, for liquid, the volume is definite. It takes the shape of the container. And for gas, it assumes the shape and volume of the container. So that's where we got the idea from. Okay. So yeah, also the molar mass of the gas is equal to the mass of the gas over volume of the gas times RT over P. R being the universal gas constant, T temperature, P pressure. Uh, Basically, this relationship is derived from the uh, ideal gas equation of state, PV equals nRT. Um, so yeah, I won't do the derivation now anymore. Um, but yeah, it's important that I've mentioned to you. You could do it on your own. Uh, PV equals nRT, such that N could be rewritten as M over molar mass, capital M. Okay. Second method is the Mayer's method. So specifically, when you read about a volatile substance, most likely you use Mayer's method, or this is what you're supposed to select. That is because it says here, a known mass of volatile substance is heated and converted into its vapor state, where it displaces an equal volume of air controlled over water. Collected rather, over water. What this phrase means is that gases are assumed to be saturated with water vapor. So, in that sense, we have this equation that you have to take note of. So, the total pressure is equal to the pressure of the gas plus, this is basically vapor pressure, the saturated pressure of water. So, this volume is converted to standard temperature pressure using the CG law as follows. So, PV over T is equal to PV over T. The difference is that this one is off air, this one is under STP. So what is standard temperature pressure again? Standard temperature, I recall this is 0 degrees Celsius for pressure that is 1 atmosphere. 0 degrees Celsius or 273.15 Kelvin. Also, don't forget the Antoine equation. This was taught in your chemical engineering calculations. Uh, Here, it's still important, no? So, P water sat in millimeters mercury. It's supposed to be in millimeters mercury. Okay? Then, after the Antoine equation, that's when you can convert mmHg into other units, no? Just make sure that right now, everything is in millimeters mercury. How? If you're looking for P water sat, then temperature should be in Kelvin. But if you're looking for the temperature, then the pressure should be in millimeters mercury. It's as simple as that. Okay? So E Euler's raised to 18.3036 minus 3816.44 divided by T in Kelvin minus 46.13. Okay? So with the volume of air equal to the volume of the volatile substance, the molar mass is calculated using the molar volume at STP. So, okay, we have the ideal gas equation of state, PV equals nRT. Then we have this. So, look at this. PV, right? V or VP equals R and then NT. They were originally here at the left side. So, that's PV equals nRT. We moved NT to the left side, transpose, and then we move P and T to the left side, so that becomes RT over P. And at the right side, it becomes V over N. I hope you can visualize it. And then, right, we have the universal gas constant, 0.08206, specifically this one, not the 8.314, since, although I think even if you use the 8.314 joules per mole Kelvin, it's still the same thing. The only difference is that your pressure should be in, uh, I think Pascal. Pascal is the SI unit for pressure. So 1 atmosphere, that's gonna be 101,325 Pascal. But aside from that, either way, this is still correct. Temperature is 273.15, in other words, 0 degrees Celsius. So after you calculate, you get 22.415 liters per mole. But honestly, there's already a table for this. Where is it? There you go. So what we calculated for is the molar volume at STP, which is 22.414. That's exactly the number that we just calculated. Uh, so aside from that, it either way, you could also memorize this, so you don't have to calculate anymore. But just in case you forget, then that's not really a really big problem, since you can calculate them anyways. So yeah, and don't forget this table. You're gonna need this for Mayer. Sorry. This is for the third method, rather. Method of limiting densities. So in this method, we use linear regression in your calculator. If I recall, that's stat. Then just choose the linear table. So here, at sufficiently low pressure, all gases and vapors obey the gas laws. And this is postulated by Lord Rayleigh and Daniel Berthelot. I think this is the same guy who came up with the Berthelot equation of state, although I'm not sure. It might be a different Berthelot. I haven't really researched much on that. Okay, so the molar mass of a gas is obtained by extrapolating the plot of the ratio of density of pressure versus pressure to zero pressure. So it's described as this. So approaching zero, no? Pressure approaching zero. Uh, Essentially, the molar mass is the density over pressure. This one, ratio of density to pressure. It's described as this. Then don't forget to multiply it by R and T. So for linear regression, this is what you see in the calculator. No? Y equals A plus BX. Um, in high school, you were taught that the equation is Y equals MX plus B. But actually, this one's more useful since uh, it it's accurate with the, how do you say this, the terminology, notation rather, of the calculator. The slope, the M, is your B. Here, the A is your y-intercept. In your high school definition, M is the slope, then the small b is your y-intercept. So that's more confusing. I suggest strongly that you stick with this one. Specifically, from this equation, the most important thing is to find A, the y-intercept, because that's exactly this one, the ratio of density to pressure as pressure approaches zero. So you can say, therefore, that the molar mass in method of limiting densities is equal to A RT, art, literally, such that A is this one. Okay? Okay. Um, let's have a break. I'll resume in a bit.